Hi, welcome to es301 Engineering Analysis. This is Chapter 7, Roots of Polynomials, Part 1. So here are the learning goals. At the end of this, you'll understand how polynomials arise from the solution to ordinary differential equations. You'll know how to divide a polynomial by a monomial. You'll be able to numerically implement polynomial division, and you will know how to numerically find all the roots of a polynomial using iterative deflation and root estimation refinement. So first I'm going to go ahead and review with what a polynomial is. And here's a definition I came up with. A mathematical expression that involves addition and subtraction and integer exponents. So let's go ahead and look at some examples. Here would be a simple polynomial. Function of x is equal to a0 plus a1x, where the a's are just constants and then x is my variable. So we have just simply addition, and we have an integer exponent. We have x to the 1 power. So this is another polynomial. We just have an extra term. I've got x, it's to the 3 power here. And again, I'm just using an addition symbol, so that's also a polynomial. Now this is not a polynomial. The reason it's not is because I've got this sine x term. This is not an integer exponent of x, so that makes that not a polynomial. This is not a polynomial either because I've got x to the 2.5 power. It's not an integer exponent, so that makes that one not a polynomial. Here's another polynomial. It's in a slightly different format, but if I was to go ahead and multiply this through, I would have an x cubed term, an x squared term, an x term, and an x to the 0 term. It would look something like this equation right up here. So this one right here is also a polynomial, just in a slightly different format. So polynomials arise from ordinary differential equations. So I just want to review with you quickly of what an ordinary differential equation is. You may or may not have had a course in this. So here's an example ordinary differential equation that arises often in engineering, where I have f of t is some function of t. It's called the forcing function. We'll talk a little bit more about that. But it's just something, it's a function of time. It could be equal to 0, it could be equal to a constant. And now I've got y, and y is a function of time as well, and so y is my dependent variable. And so what I'm going to be looking for is solutions of y, and I've got a first order and a second order differential of y. So let's talk about some instances where these might arise. Here's a mechanical system that the solution to would end up with an ordinary differential equation. If I was to look at what the displacement is, for example, of this bottom lever here, where I've got a series of springs and some damping pots on it, and so depending on what the characteristics are of those, I'd be able to determine what the displacement is of the bottom, and to find that solution that would originate from an ordinary differential equation. In electrical engineering, if you've got circuits that involve capacitors and inductors, you end up with ordinary differential equations. If you're solving, for example, the voltage or the current. In environmental engineering, if you were to look at, for example, what the concentration of a gas or a pollutant is in the atmosphere, where you've got reactions occurring, where you've got ozone depletion or ozone generation, you've got wind going on, that could all originate from a or be described by an ordinary differential equation. And in geological engineering, if I was to look at here, I've got some radio sounding going on where I've got attenuation of the signals as it propagates through this material and it reflects. And this also could be described by an ordinary differential equation. So they arise in very many aspects of engineering. I want to talk about what the characteristic equation is. And so here I've got my differential equation again. What I've done is I've set this forcing function equal to 0. So that means that it is unforced. And so what that means is, for example, let's take the mechanical analogy in the previous slide. It means that what I'm doing is I'm looking at what the response to the system is if I'm not constantly pulling down and pushing up, for example, on the bottom lever or at the top. And so I'm just going to go ahead and maybe just pluck it and then see how it evolves with time. So that would be an unforced equation. So I set this equal to 0. And I want to go ahead and solve this. So now what I want to do is I want to find out what is y of t. And the solution to this is, well, it's going to be in the form that y is equal to the exponential to some value r times t. Now if I was to go ahead and take this solution for y, plug it into this differential equation, I would end up with this. So you can see I've got my first order differential, my second order differential. That term arises from the first order, and the second order, here I've just got a0 times my value of y. And what I want to do now is I'm going to want to figure out what my solutions are for r. And so what I end up with is what's called the characteristic equation, where I have a0 plus a1r plus a2r squared equal to 0. And then I want to determine what my values of r are by solving essentially this characteristic equation, right? And you can see it because you just go ahead and cancel out e to the rt of this equation and end up with that. But notice that y, right, is equal to e to the rt. The value of r says whether the solution is going to, for example, blow up or decay in time, depending on whether r is greater than or less than 0. So my solution, if this is as a function of time, if I had a positive exponent, it would look like that. If I had a negative exponent, it would look like that. So this, the sign of that exponent matters, and how quickly this occurs is a function of the magnitude of that value of r. I want to talk a little bit more about these constants, and so this kind of gives us a rise of the damping behavior. So I'll reproduce the characteristic equation up here, and if I want to determine what my roots are of this polynomial, so I want to figure out what my values of r are. Here's my quadratic equation, and so using the constants a1, a0, and a2, I can go ahead and determine what my constants of r are, and that gives a rise to a couple different types of behavior that you can get. So if I was to look at what my response of y is as a function of time, it turns out you can get 3 different responses. You can get something that's called an overdamped response, and so if the response of my system was to quickly decay down to 0, this would be considered an overdamped case. There's something called the critically damped, which means it's going to go ahead and oscillate, and it doesn't get smaller and doesn't get larger. It just kind of evolves with time that way. And then there's something called the underdamped case, where it decays to 0, but it also has some oscillations. And so, for example, it might look like this, and this would be an underdamped case. It all depends on the magnitude of these 2 values of r, right? There's 2 values of r that come from here, depending on what those are. And so looking at this any further is a little bit beyond this class. I tend to look at it in measurements class, but it's important to kind of understand where this might originate from. So remember, this response here, back to my physical systems, it might be what the displacement of that bottom lever was, or what the voltage is, or what the concentration of the gas is with time. Is that concentration of that gas increasing or decreasing, and does it tend to fluctuate? Alright, so there's some background of why we care about polynomials, but now what I want to do is I want to talk about polynomial deflation. So here I have this 5th order polynomial f of x, and so if I wanted to go ahead and look at this and ask you what are the roots to this equation, right? If I was to go ahead and set that equal to 0, and I wanted to know what the roots of that equation are, it's not really obvious. Now if I was to rearrange that function into this format here and ask you what the roots are of the equation, what are the values of x that would set it equal to 0, it's very simple for you to see. Well, over here, if I just went ahead and said it was minus 1, that would make this first term over here equal to 0. That would set the whole thing equal to 0. So clearly I can quickly see what my roots are. My roots are going to be minus 1, positive 4, positive 5, negative 3, and positive 2. Right? So it's really easy to see when it's in that format. So it would be nice if I was to go ahead and factor and determine what it is. And this is what we're going to do. And we're going to do them one at a time. And effectively what we're going to do is we're going to find one of those values and then deflate this polynomial. What I mean deflate is I'm going to go ahead and divide it by, for example, divide it by x minus 4. And you can clearly see if I was to do that, what effectively I've done once I've found this root, I remove it, I end up with a new polynomial, and then I'm going to go ahead and find another root and then deflate it again. So there's the idea of deflation. So before we go ahead and do it with polynomials, let's just go ahead and review a little bit of long division. You can probably remember this from grade school, for example. So I've got the number 1281. I'm going to divide it by 7. And how do I do that? Well, I look for the largest factor of 7 that will go into, for example, 12. And that would be 1. I'm going to put up on the top. 1 times 7 is 7. And I'm going to go ahead and subtract that. And so I have 5, bring down the 8. And now I've got 7. The largest that will go into that would be 8 times. 7 times 8 is 56. The difference of that is 2. Bring down my 1, and then I end up having 3. That's 21 with a remainder of 0. So my remainder is 0, and it's 183. So 7 times 183 is going to be equal to 1281. So that's how we do long division. And now what we're going to do is we're going to do the same thing, but we're going to do it with polynomials. So let's look at how we do it with polynomials. Okay, here's my function that I want to do. And now what I'm doing is I'm effectively deflating it. I'm dividing it by this x plus 1 term. And so how do we do it? Well, we're going to do a similar idea. I'm going to have an x squared first. X squared times x is x cubed. X squared plus 1, so it's going to be plus x squared. And now what I'm going to do is go ahead and subtract those two. So I've got a 0 there, and then I have plus 2x squared left over, and then bring down my minus 10x. And now again, I'm going to go and look for my division. And so I've got a plus 2x in the top, 2x times x, 2x squared plus 2x. Subtract that 0, and now I'm going to go ahead and subtract 2x from minus 10, so I have minus 12x, and then bring down the last I have, minus 24. So now I've got minus 12x. So what I'm going to do is just do minus 12 up there, minus 12x, and then I've got minus 12. And so then if I go ahead and subtract that, and what I have now is a negative, I'm going to subtract the negative 24, and then a positive 12 effectively, so this ends up with minus 12. So what I have now, though, is I have a remainder of minus 12 when I did this division. And the important thing to note here is what that means is that this x minus 1 was not a factor of that polynomial because I had a remainder. If I didn't have a remainder, then it would actually be a function. So effectively what I'm doing, let's just look at, so this is my polynomial I have here on the bottom. What I'm trying to do is find these values of t, right here, at t1, t2, or t3, that ends up so that I would have a remainder of 0. And what I did effectively is I guessed that it was equal, that my term was x plus 1, or that t was equal to minus 1. But since I had a remainder, it didn't work. So what I need to do is effectively just go ahead and guess that again. So there's kind of the numeric idea of how we're going to go ahead and do this. All right, so what I want to do is look at this pseudocode the book provides, which I got right over here, I've reproduced on the upper right. And what I want to do is step through this and see how this is effectively does the exact same thing which we just did with that polynomial division. It's not real obvious though, so I think it's kind of important to go ahead and step through it. And one of the things to remember is that the value of t was that root, and so effectively I said that t was equal to minus 1 because I had x plus 1, and it was kind of my guess. And the reason that we're using t here for the roots is because the book is using r for remainder. A little bit confusing, but just remember t are the different roots that we have. And what we're going to do is we're going to go ahead and step through this pseudocode. And so what effectively this first line is doing is we're setting the value of r, the current remainder, equal to a to the n, where n is the largest value of my polynomial. So n is equal to 3 in this example. So that's my highest exponent in the polynomial. And then what I'm doing is I'm setting a of n, which it starts off at 3, equal to 0. So what I've done is I've just removed this largest factor at the top. And if you kind of just step back, we can see why that is, right? When I'm doing my division, clearly I don't have any x cubed terms, and so I would go ahead and set that equal to 0. Okay, so that's what I have. And now what I'm going to do is now I'm going to step through. I've got this counter I, and it goes from n minus 1 down to 0, and the step size is every minus 1. This is pseudocode. This isn't straight MATLAB. That's why it looks a little different. Okay, so we start off here. We've got I is equal to 2, and we have S is equal to A sub I. And so what that means is S is going to be equal to the value of A2. Remember, those A's are the exponents that I have there. So A2, and A2 is equal to 3. So what I've done is I've set A at this value S to 3. And this is just a placeholder. You'll see why I need it, because I need to hold on to it. The reason I'm doing it is because now I'm changing the value of A sub I. I'm saying A sub I is equal to my remainder. Look back to what my remainder was. My remainder was initially the exponent over here, which was 1. And so what I've done is I've set A2 is equal to 1. So this is kind of my new polynomial that I'm building, the new values of A, of what my division is going to be. All right? And then the last step here is I've got to determine what my new value of R is. And it's equal to what my value of S is, which I held on to. It's equal to 3 plus my value of the remainder. The remainder started off at 1. And then my value of t up here, right? There's my value of t, and it's equal to minus 1. And so this all ends up being equal to 2, right? Okay, now what I'm going to do is I'm going to go back through my loop. And so now I is going to be equal to 1. And so S is equal to A1. And what that right there is equal to is minus 10, all right? And now I've got what is A sub I, and so A sub I is equal to what my remainder was, and so A1 is going to be equal to 2, all right, because I went ahead and held on to that. And now I need to calculate a new value for the remainder, and the remainder is going to be equal to minus 10 plus 2 times minus 1, my value of t, and that right there is equal to minus 12. And so now I've got one more time through the loop when n is now, or sorry, I is effectively going to be equal to 0. And so s, which is just a placeholder value, is equal to a0. And that one right over there is going to be equal to minus 24. That's the last term up in that equation. And then I go ahead and find my new value of a0. And a0 is equal to minus 12. And then the last thing to go ahead and do is find my remainder. And my remainder there is going to be equal to what the value of s is, which I held on to at minus 24. And then plus my value of r, which is minus 12, times the value of t, minus 1. And that all ends up being equal to minus 12. Okay? So what I want to do is kind of point out, okay, look at my remainder values. It's minus 12, this minus 12, and this value of 2. If I go back, you'll see that minus 12, and that value of 2. So those were those remainder values that I had. But notice that this right over here at the very end is minus 12, which is the same remainder that I had, which means that x minus, or value of t minus 1, or essentially the monomial of x plus 1, is not a factor of that polynomial. So what I need to do is I need to go ahead and adjust that value. So what I need to do is I need to go ahead and determine a new value of t. And I'm going to do that using a first order Taylor series approximation. And so what I've got is I can say that r, if I was to adjust my guess value of t plus delta t is equal to what r was at t times dr dt over delta t. Let's just go ahead and rearrange that, because what I want to do is I want to adjust the value of t. So I want to find out what delta t is. And delta t is going to be equal to, well, right, I know that I don't want a remainder to be equal to 0. So now if I go ahead and solve this, delta t is going to be minus r over dr dt. All right. And now the first time we did this, our value of r was equal to, right, was equal to minus 12. Right. And I've got a minus up in there. And now I've got this dr dt term that I need to go ahead and determine what that is. And so let's look at how we find out what dr dt is. And then what I'm going to do is return to my pseudocode and look at particularly that line right there where the value of r keeps changing. And remember, I'm trying to find dr dt. And so I can go ahead and get an expression for that. Let's go back and look what we had. And we started off when I was 0. So in fact, I'm going to unroll this. We said that r was equal to s plus r times t. Okay, and this was at that very last time, so that was more or less s0. And so what I want to do now is if I go in and look at what the previous value of r was, this is equal to s0 plus, and what was r? Well, r was equal to s1 plus rt, and that times t. And if I do that recursion one more time, I have s0 plus s1 plus, and now I've got s2 plus rt times t times t. All right, so now I have a value of r. What r is a function of t. This is r as a function of t, and so I can go ahead and take the derivative of that. So let's go ahead and just multiply this out first to go ahead and see it. So r is going to be s0 plus s1 times t plus s2 times t squared plus r times t cubed. All right. And now I can go ahead and take the differential of that. So I'm going to take what dr dt is. Dr dt is going to be equal to s1 plus 2s, this is s2, plus 2s2 times t plus 3rt squared. Right? And now what I do is I'm just going to go ahead and plug values in there. And if I go ahead and plug values into this, so I'm going to take my value of s1 and s2, my current value of the remainder, and my value of t, I find out, I'll go ahead and let you do that, that comes out to be about minus 40. So that's what I'm going to go ahead and put in. Let's go back to our previous slide here. So now this value right there is minus 40. So now I know what my delta t is. My delta t over there is going to be minus of a negative 12 over negative 40. So that's how much I changed delta t. So now I'm going to have a new value. I'll call it t new is going to be equal to t old plus delta t. Okay. Previously I guessed that t was minus 1. I'm going to put this value in there. I'm going to find a new value of t, and I'm going to guess a new value in terms of my polynomial. And I keep doing that until I get a remainder that's equal to 0. And at that point, I've completely found that factor. So this is how you numerically find the factors of your polynomial. All right, so let's go ahead and review what we looked at in this video. We saw that polynomials arise from solutions to ordinary differential equations. It gives rise to something called the characteristic equation. We looked at a second order ordinary differential equation, and when we do that, the root values determine the damping behavior of the systems. We want to find the roots of polynomials, and roots of polynomials can be determined one at a time numerically, and what you'll do once you find that value is the remaining polynomial you end up deflating by 1. And we also saw that we can use a first order Taylor series approximation to refine our guesses for our roots, and we do that until we have arrived at the root that we're looking for, and then we deflate the polynomial by 1 and go forward. So I know it seems kind of complicated, but what we've got is a numeric system to go ahead and find the roots to an equation, and you can do this for very, very large polynomials.